or negative, our supposition there is that 0 is an intermediate value between positive and negative values. And because the expressions we're looking at are continuous, right, we know that the sign change has to happen at where it's 0. I mean, really, the intermediate value theorem is behind that whole sign chart method we use, truth be told. Now, there's a very ancient method of solving equations that's based on this, right? It's called the method of bisection. Do you guys know the method of bisection? So I have another, please do read the rest of the notes here. I have like three more examples that I haven't actually put on the board because, as I told you guys, I foolishly spent too much time on how to factor polynomials in here this semester. My apology. As you read the notes that, example 2.6.4 and example 2.6.5, if you have questions about those, feel free to bring them up in a future class and we'll address them, right? You just got to ask, okay? But the method of bisection basically is like, so we have figured out that between 0 and 10, somewhere in here, there is a solution, right, to this problem. Equal, right? So what do? You pick the middle point, right? You pick 5, right? And check f of 5. What's f of 5 equal to? Now I'm starting to regret not bringing my calculator. 5 to the 5 power, which everybody knows, plus 4 times 5 squared. Well, 4 times 5 squared, that I can do. That's 100. So this is 100 plus 5 times 620. I know 625 is 5 to the 4th. Because 5 cubed is 125, and 125 times 5 is 625. And 5 times 625 is 3,000 plus 3,125. I believe this is 3,225, if I haven't made an arithmetic mistake, which is anybody's guess, right? Did I get it? Cool. So what is 3125? Is that plus 100? So, yeah. So where is the solution? Which half? So this implies, see, f of 0 is equal to 0, is less than 100, is less than f of 5, which is 3225, right? So that means we have narrowed the scope, right? That means that the solution, it's got to be up in here somewhere, right? So what do you do next? Go down further, right? You bisect again, right? So we look at the midpoint of that. 2.5, right? What is f of 2.5? 2.5 to the 5th power. Plus 4 times 2.5 squared. You'll have to tell me what that is. I don't want to. Oh, you were using your phone, weren't you? I guess I could do that. I do have a phone. 2.5 to the 5th power plus 4 times 2.5 squared.
The answer is approximately 122.66.
If we trust Google, 122.66 approximately, right? So what's that show? Yeah, that shows that the answer is in here somewhere, right? So next we check f of 1.25, right? (1.25 to the 5th power plus 4 times 1.5, 1. Let's try that again. 1.25 to the fifth power plus 4 times 1.25 squared?
The answer is approximately 9.3.
So what did we figure out? The answer is somewhere in here, right? The solution to this, there's a 0 somewhere in there. Not a 0, rather, a place where the polynomial output's 100, right? This is not something you haven't done before, right? Maybe you didn't call it the intermediate value theorem. You called it using a graphing calculator, zooming in to find out where the function takes a particular value, right? Maybe you did that in your high school math class or something. But that's essentially based on this idea of bisection. And there are computer algorithms that solve equations using this method. I mean, it's pretty low tech, right? But it gets to it. All right. My example 2.65 is a little bit different. You notice that all of these things we're saying fail if you have a discontinuous. Again, discontinuous one. So like, see this? If I had a function, right, and the graph looked like this, if that was my function, you know, this is A, and say over here is B, right? So this function is what? Not continuous, right? And it's not continuous. And if I was to take the intermediate value, like right here, we'd be out of luck. We wouldn't be able to find a C such that f of C is equal to that n. So continuity is an important, it is an essential feature for the intermediate value theorem to actually work, all right? Okay, so in the time that remains, I'm going to at least get us started on the derivative and the tangent line. So we'll talk more about it tomorrow, right? We have a lab tomorrow, which is all about finding tangent lines and so forth, and visualizing them. So we'll do that. But for the moment here, let me just give you a definition. If f is a function whose domain contains A and the limit below denoted exists. So here's the limit. Limit as x goes to A of f of x minus f of A over x minus A. All right. Then we say f prime of A is equal to that limit. And f is differentiable at A with tangent line y equals to f of A plus f prime of A times x minus A. So this is the definition of both the derivative at a point, which we call f prime of A, as well as the tangent line. So when a function is differentiable, the tangent line exists, and the slope of the tangent line is given by the derivative. All right? I'll do a real simple example here for you guys. Just to wet our whistle. So f of x equal to, say, x squared plus 1, right? So f prime of a, limit as x goes to a of f of x minus f of a over x minus a. All right, so what is that? So f of x is x squared plus 1, right? F of a is what? We got to put a in the place of x, right? So subtract a squared plus 1. Divided by x minus a. So what we got then is x squared minus a squared over x minus a. What kind of limit is that? Type what? It's type 0 over 0. So these determinant limits, they're always going to be like this. The determinant limits, they're going to involve 0 over 0. Like, it's just going to happen. It's the nature of the problem. Now we can factor x minus a squared, x squared minus a squared. How's that go? I think I got about 3 homework problems which are more or less like this, but with numbers. So this is x minus a times x plus a. See what happens? So the x minus a's cancel, right? And what are we left with? X plus a, right? But plug in a, so we get a plus a, which is 2a. Now, for the sake of graphing, let me make it a little bit more concrete. So consider a equals to 1. So we'd have y equals to f of 1 plus f prime of 1 times x minus 1, right? Which is 1 squared plus 1 plus 2 times 1 times x minus 1. That's 2 plus 2 times x minus 1, right? But that simplifies to just 2x, because you got 2 minus 2. So y equals to 2x is the equation of the tangent line to this function at 1. Here's a graph of what's going on. So you guys know how to graph x squared plus 1, right? It's a parabola, opens up, y-intercept of 1. Looks like this, roughly speaking, right? And at x equals to 1, about right here, we have the tangent line that looks like that. The point of tangency is right here. It's the point 1, comma 2. So this is the best linear approximation to that quadratic at that point. And we found the slope of the tangent line using the limit of the difference quotient. So we're going to do this over and over and over again for a bunch of functions. But that's it. Like, if this limit exists, the function's differentiable. It doesn't have to exist for all functions. There are functions where this doesn't work out. But many functions do have a tangent line at a given point. So anyway, tomorrow we will look at it more with computers. Thanks, guys. Also, I need your